So today, this is some joint work with Pascal Poupart on satisfiability and Markov decision processes. So the overview of my talk, I'll go over the reduction from stochastic set to POMDP, and then from POMDP to stochastic set in the reverse direction. And I'll cover two components from stochastic set solver using decomposition and symmetry detection. And I'll go over a benchmark on POMDP problems. So what is satisfiability? So it's essentially to determine if a joint assignment of a Boolean formula evaluates to true. So in this example, we usually work with Boolean formulas in conjunctive normal form, where each formula is a conjunction of clauses, and each clause is a disjunction of literals. So in this case, the solution, one possible solution is x1 and x4. So in general, SAT is a very broadly studied problem. There's various applications in bounded model checking, classical planning, scheduling, etc. There's also been many extensions to SAT, including sharp SAT, SMTs, quantified Boolean formula, and stochastic SAT, which would be the focus of this talk. So what is stochastic SAT? It's essentially trying to find a joint assignment of variables that would maximize the probability of satisfying a formula. So in this formula below, stochastic SAT introduces a new quantifier called randomized variables, where existential variables, you get to choose what values they should take, and randomized variables are sampled from a distribution given by the problem. And these are usually encoded in pre-mixed normal form, which means the quantifiers are pulled out to the outer block, and inside the Boolean formula is in conjunctive normal form. So stochastic SAT is the complexity is in space complete, similar to quantified Boolean formulas. And similarly, POMDPs are also in this complexity. So what exactly is POMDPs? So a simple idea is if you have an agent in an environment, and they can take actions from some action space, and the environment is in some particular state, and you get a reward based on the action taken and the current state of the environment. But you do not get to observe the environment. Instead, you receive an observation that's correlated with the state. So the difference between a POMDP and, say, reinforcement learning, you get to observe, or you know the models. So in particular, the transition, distribution, observation, and the reward function. And here we work with finite horizon POMDPs. So what sort of motivates my work is being able to trying to encode POMDPs and stochastic sets since they're in the same complexity class. So the idea here is, given a stochastic set problem, how do we encode it to POMDPs? And one idea is to assume that we have a stochastic set problem that has an alternating sequence of existential and randomized variables. Then the actions in the POMDP would correspond to assigning existentially quantified variables, and the observations in the POMDP correspond to assigning randomized variables in stochastic set. So the reduction goes as follows. So in the POMP, each clause it becomes a state plus two additional state, stat and prob. So essentially stat represents the idea that the formula is satisfied, and prob is sort of a partial, the probability of the partial assignment up to that point. So we have a uniform distribution over the initial belief. And for the action space, at each time step, the action corresponds to an existential variable that's been assigned true or false. And so the transition dynamics will be deterministic, where if you're in one of the states CI and you make an assignment AT, then if that clause CI is satisfied, then you transition to the satisfiable state. Else that clause was not satisfied by the assignment, so you stay in that state. And the identity transition for the other states. So similarly for the observation distribution, you receive a particular observation at each time step, which corresponds to sampling from the observation distribution in stochastic set. And we want to do something similar for the transition function, but you cannot move probability mass directly. So what you can do is have a 0 or 1 to remove mass from a particular state. And the prob state essentially keeps track of the partial assignment. So lambda would be the probability of this particular variable being true in this stochastic set problem. And 1 minus lambda is the opposite. So for the reward, it's interesting because it depends on time, where after assigning all the existential and randomized variables, at the end of that, there's a final phase where a reward of S is given for the prob state, which essentially means that if you have some probability of satisfying the formula, then you'll get a certain reward, which cancels out the 1 over S in the initial belief. And if any of your states or any of the components from your belief is in the CI state, that means the formula was not satisfied, and you get a negative reward, which you would then choose a positive action, AT equals false, and get 0 reward. So in general, the horizon is half the number of variables, because at each time step you assign existential and a randomized variable. In the opposite direction, we look at transforming POMPs to stochastic set. And here we'd like to encode all the parameters, so the probabilities and the reward function of the POMP into a randomized variable. And we'll focus on horizon 1 case for POMP. So the optimal action to take would be to assign all the actions and choose the action that maximizes this expectation. So we can encode this into a stochastic set problem by first doing policy selection and then policy evaluation. So in policy selection, we first use an existential variable for an action, since we're maximizing over actions, and then a randomized variable to encode the current state we're in, and a randomized variable to encode the reward of being in that state. So the domain of the randomized variable XR would be now be a probability distribution over A and S that sums to 1. And so in the policy evaluation stage, we can encode the formula 4 as this Boolean formula, where it's essentially saying that if your if you take action K and you're in state I, then you'll get a reward of R, XR, where the value of XR corresponds to the distribution in equation 7, which is the reward function. So the general case for h greater than 1 is in the paper if you'd like to take a look. So in summary, for both encodings from stochastic set to POMP, the complexity of the states is essentially the number of clauses, and the horizon is proportional to the number of variables. And from POMP to stochastic set, you have the complexity of the number of variables depending on the horizon, the action, times the state and observation plus observation. And similarly for the number of clauses depends on the horizon, the action, the state as well. So now I'll focus on stochastic set solver. In particular, one of the techniques used is component decomposition, where essentially if you have a formula, F here, you can actually decompose it into separate components that can be solved independently. And so if you have a set of these components G, then the probability of the entire formula can be factored into this product. And this is a huge reduction in complexity. However, especially for structured problems like POMP, a lot of the components are symmetric and are essentially the same solution reworded. So that sort of motivates the use of symmetry, where different components essentially have the same probability of satisfaction. So we need to detect these symmetries and deal with them. So one way to do that is to, in the SAT literature, is to have some sort of ordering. But in this case, we need to enumerate all solutions. So we cannot just pick one in particular. So one idea is to use a graph isomorphism. So if we can encode each component into a graph and use the canonical representation of that component as the primary representation in the solver, then whenever we see this component again, it will be mapped to the same representation. So in the previous example, this is encoded in the top right graph as two components. Now, if we were to assign x3 to a value, that would split the first component into two. And we notice that all three in the bottom right components are actually the exact same. And so this is using graph coloring where different types of nodes have the same color, and then those colors are exchangeable. So values, variables, and clauses are exchangeable with each other. So graph isomorphism is actually, for some graphs it's easy to solve, but for others it's very difficult. And so in our solver, we implemented different variants of this. So I'll show some results. So the first variant just does traditional component decomposition, and then we looked at the full graph isomorphism problem of the canonical component decomposition with symmetry, and then a simple projection of the graph that I showed earlier, just renaming the nodes, called CP. So overall, the canonical representation was too costly on most of the problems, but a simplified version had a lot of improvements over traditional component decomposition. And the final experiment, which is again a POMDP problem from the Cassandra website, compares War, Raven, and Prune, which is an exact native POMDP solvers, versus Prime, our solver, where we encode POMDP problems into Stochastic Set. So these are 13 problems from the benchmark over 10 states. And here we were able to get a higher horizon or lower time on 8 out of the 13 problems. And Xander is another Stochastic Set solver. So here, Prime was able to be efficient on a lot of these problems because it searches the policy space directly, whereas War, Raven, and Prune, when there's not a compact representation using alpha vectors, they tend to fail. So in conclusion, we show a constructive reduction from Stochastic Set to POMDP and the reverse, and shows one of the components in our solver Prime, along with some empirical comparison with native POMDP solvers. Some future work we would like to look at is extending some previous techniques from SAT, model counting, and QBF to Stochastic Set solvers, and sort of look at different techniques that's being used in POMDP solvers and see if those which are orthogonal can be implemented on Stochastic Set solvers.